Sam, but he might be okay. He sometimes forgets that we have class at this time because his brain.
So he is ready to be a faculty. There is a superstition that it is a professional disease, absent-mindedness.
Oh. I feel like that's a disadvantage for a faculty member.
But it is like after you work long. Well, it shouldn't be true, but it is like a joke.
See, my hypothesis about planning is correct.
So should we send him a reminder?
About planning?
Yeah, because he was like, this APS was very organized. We have our plane ticket and our hotel 2 weeks before.
Wow.
And then I said, Jabed and I got our MRS a month ago for a month to go. And then he said, oh, if I had to do your organization, it would be a rhythmic scale. I was like, it can be time dependent. So as you age, you get less and less order.
So when Svetlana reminds us, she doesn't remind you too?
when I remind students in like South Dakota, and I usually do it like 3 months before I would do something myself.
Usually that's when I start panicking, when I start getting reminders. Oh, it's time to do it now.
Oh, very happy to see you. Thanks for coming, and thanks for those of you who submitted homeworks. If you didn't yet, do not rush. You can do it after the class or later
I
during the
write
day.
that one.
Huh?
I write that answer, but you don't send you yet. Just have to answer one question.
Just find time to. So, next time we see each other on Thursday, it will be a fun day, because everyone will present very interesting applications of time-dependent perturbation theory. I know that some of you have chosen or were encouraged to choose very challenging tasks, which are extremely hard to present in 5 minutes. But let's try to do whatever is possible to get a general exposure of why time-dependent perturbation theory is needed and how it can be applied. Everything we do in a regular class is like 10-20 times easier than the subjects that you guys will present. You will do like very advanced topics. So, who we are, what we are doing, and what is our plan for today. There will be nothing new today. It will be basically corrections of errors that were made or that were about to be made during the last lecture. So we are finishing Fermi's golden rule, discuss its applications, enjoy the math behind it, and then we are done. Should be quick. So we will discuss simple math, approximations, and analyze the solution within like half an hour, maybe 40 minutes, and then exact time measurement is not a good idea, like during 60% of our class time. And then at the rest, if you have steam, you will enjoy complex calculus. Complex not because it is very complicated, but complex meaning real and imaginary. So if we skip this last part with this little mathematical exercise that I leave as a dessert for today's class, you will miss nothing. It is just a table integral that you can get from the internet. So unless we live on the inhabited island, we do not need it. So you just enjoy a little exercise. And it is the only handout I want to distribute. So it is a reminder, if you were taking calculus in complex variables already is a little introduction if you were not taking it. While preparing today's meeting, it took me more time on this mathematical supplement rather than the compared to actual scientific part of what we are doing. And the idea here is the finite integrals over the finite limits that going along the circles in the complex plane. And there is a very practically quick and simple way to find values of complicated integrals in a couple of minutes. But if we are introducing this technique, it may take a little longer.
Is this a subject that Kieran Beck was talking about during his?
Yes. It is the I don't know whether it's true or not, but he was claiming that his advisor, Walter Kohn, was not originally trained in complex analysis, and he was bragging that he communicated him part of this theory, which I'm not sure it's typical part of.
I thought.
Where did you?
Or maybe otherwise.
Canada.
Your own
Where was it, Canada? Nice. And he was talking on complex.
No.
No.
He was talking during the memorial. Well, he was talking about using chem informatics for designing functionals for his official talk, and then during the banquet he was giving memorial talking in memory of Walter Kohn, who was his thesis advisor, and this talk was really good.
When did Kohn die? Because I thought he was still alive.
Last
That's
year.
last year.
Oh.
So we are so lucky that we are meeting for the 15th time in this semester, in this environment, and administratively, so you are bringing in work number whatever, about 4. We will tomorrow at March 8th we will have a lab which will be shorter than usual, and on the March 9th there will be presentations. So noon, please send the PowerPoint files like midnight before. So March 8th midnight, send your slides. So we are going to finish the chapter of time-dependent perturbation theory today and on Thursday, but we are not going to give up the time dependence. We are going to look from the evolution of quantum systems in time from different points of view with different theories after we return from the break or from the American Physical Society conference. So next week will be no class because of the break. And then we will start a new chapter. So scientifically, we're not going to do a detailed review, but if there is a little perturbation that is time dependent, then occupations of the states change with time. And we found that first order is already powerful enough. In the homework, we found that if it is on resonance, it grows quadratically, and it is maximal change. If it is away from resonance, it is less influential, but still some change in population. And we are going finally prove that there is a specific case. If we modeling transition from one final state to several, from one initial state to several final states which are spaced very densely, which are represent continuous distribution of final states. And if you have discrete amount of final states, then probability of transfer, the occupation of final states and de-occupation of initial state goes quadratically with time. If you introduce continuous distribution of final states, then the dependence will be linear. And we are going to make a mathematical effort to prove. What we are going is called Fermi rule. If you have time, we will do Lewis theorem, and we will prove that sine square x over x squared dx equals pi. And if there will be no time, we will leave to this table integral. So we need to complete several simple steps. So we will recall last expression for population of either excited or initial ground state as a function of time. Closer to the end, we will make derivative of either one of them over time and call it rate. And we will analyze consequences and examples, such as subject that Javet will present in 2 days. Spontaneous emission. So in between, there is a critical thing that we need to focus. In most of the textbooks, as soon as you get the application of time-dependent perturbation theory towards population, then one tells that there is an integral and one goes immediately to the rate. And the intermediate steps are skipped to the level that they are not reproducible. We are going to reproduce them and see what is the origin. How do we get from quadratic to linear change in time? So there is a choice of integration variable. And then, due to this choice of integration variable, the equation for this population is enriched with time as a factor in some power. And this actually makes change in the dependence. And then we do integration using this table integral and get to analyze the answer. So it is just a very brief sketch of what we are going to do. And during the derivation, we may accumulate error in some prefactors in constants. So when we get to the end, we can look again and correct it. But the goal is to get linear dependence as function of time. So let's let's declare the answer first, so that we know where are we going. So interaction Hamiltonian. Square then fundamental constants, then density of final states. So if we have initial ground state and a lot of final states, where there is a transition frequency and there is a operator of transition. For example, this could be type of interaction with electric field. So if our system can be classified with this schematic diagram, then the rate of transition from initial to final will be proportional to the absolute value square of the matrix element of the interaction in the basis of initial and final states. Final states are assumed to be very similar to each other, times the density of the final states. And the density will decrease linearly with time at initial steps. So if you agree with these statements, and again, there could be like 2 pi coefficients in front that we can carefully check. I fairly not sure about pi or 2 pi.
2 pi over h bar means Fermi golden rule usually.
Good. We will check what we will get at the end of today's meeting. Maybe we will get something crazy like 4 pi over h bar squared if you do some errors. Hopefully not. So if you agree with this settlement, with this equation, then it means that you are acquainted with Fermi's golden rule. It is very general and it is applicable in the limit when the inducing frequency is tending to 0. You can assume that there is no energy offset between initial and final, and still apply this Fermi golden rule. There could be different variety of the nature of these quantum states. But one of the earlier applications was the quantitative description of the photo effect. When one photo excites the metal and goes into the continuum of the unbound electrons, the electron leaves the surface. Therefore, one needs continuous distribution of final states. Okay. So all excited states as function of time summation is not equal to 1, but all other states C and in the ground, in the initial, it will be 1 minus P. So when we met last time, we explicitly wrote down the expression based on the first order time-dependent perturbation theory, found that it contains a combination of oscillating exponentials, and combined it into sinusoidal function, missing some off-resonant terms. What did we have in front? So matrix element from state 1 to state n of the transition dipole and strings of electric field, so totally square. And let's put constant c. Otherwise, we will spend time on figuring out the exact value of pi over h bar, but let's clean them up later. Put all constants as c here. So if there is a discrete summation, and then this function at short time shows quadratic growth. And if we add together discrete number of such functions, they will still show quadratic growth. But the trick is in the transition to continuum. So we are going to replace summation into integral over frequencies times number of density of states. So summation of something is equivalent to integrating the same something where this integration includes number of states per given interval of energies. So if we have one electron density of states that comes out from typical quantum chemistry calculation, DFT, you have Fermi energy, you have conduction band, you have valence band, and approximately in the non-interacting orbital approximation, you have the gap, right? But then you can analyze the same system. Here is general system with continuous bands. You can analyze the density of excitations. So we also neglect formation of violent excitons, and so that if the energy of ground state is zero, then energy of first excitation will be this much minus this much. And then as higher the energy, the more states will be available. Make sense? So now let's assume that we have model. So this is one electron states, here is minus k. Or we can tell that h bar omega and k. Now let's consider the situation where we perturb this system at frequency omega. And it could be mathematically comfortable. In what follows, there will be zero scientific, zero science, only math. So it will be comfortable, mathematically comfortable, to shift the origin, place the origin near the center of the inducing frequency. So we are plotting density of states of excitations, but it is shifted. So I'm rewriting the same picture, but here I'm telling that it is omega and k minus omega capital, and this point now will be our zero. So we are excited dose. So we are going to look at number of available transitions, number of available states in the vicinity of the center of excitation. And if you want to plug it into our derivation, which is general, we do not keep in mind specific systems. We can call this range as n of omega minus omega. Or we can swap the same. So let's rewrite our expression for population in all final states, or summation, or now integration over all final states with this new notation. So before we did this notation, we had constant integral d number of states, then this matrix element of interaction. Seems clear. So we were looking on the states in the vicinity of the central frequency. Now if we change the variables of integration, nothing changes except that we will be integrating from minus delta to delta. Minus delta. T omega k. I think if we had energy here and we have frequency there, we need to add one h bar factor. just omega number of excitations shall be n and 1. N and 1. Square of transition matrix element, and then this function. So the goal is to simplify and take it, simplify this integral to such situation that we would be able to apply it to any system with any specifics without much complications. We cannot request users of this approach to take integral over and over. We can take maybe an approximation in the vicinity where the density doesn't change much and function behaves in a predictable way, and compose the answer as like product of simple things. We do must they, and then all applicants will do, all people who apply this theory, all users will do it quickly. So there will be another change of variables, and what else? Since we want to simplify it for users, it would be nice if you could take the density of states out of integration and matrix element of interaction also out of integration. How can we do it? Or in which limits can we do it? Well, we can tell that our we can tell that the density of states is the central value at the point of resonance plus its derivative times the offset. And if we are staying in the limit very near the resonance, we can neglect this correction. So we can assume that in the vicinity of the resonance condition, density of state is homogeneous. It doesn't change much. Also, the transition dipole, we can assume that it is homogeneous transition dipole. We consider several excitations and they all have similar values of transition dipole, which is not a super nice approximation if we do quantum chemistry with few levels, but as something very general, it is okay. So homogeneous density of states and homogeneous transition dipole. So we place T constant minus delta constant D. Oh, I shouldn't write it. First I should put all things that we placed so all information that specifies practical system is placed outside of integral. And the rest is just a chance to practice in math. So integral omega 1 equals capital sine square our main goal hasn't been done yet. So we are within the major challenge. So it is just a couple of lines to do, but I was about to miss this part last time, but today, no. So we are going to use a specific selection of the integration variables. These were system specific, and this one is genuine. So we are going to go into crazy paradoxal way. A minute ago, we assumed that delta is so small that we are working in the vicinity of the resonance. Therefore, we can assume that density of states can be taken out of the integration. No one was objecting, meaning it is accepted by the community. Now, we are doing opposite limit. Let's consider that delta goes to infinity for mathematical comfort. So it doesn't mean that we physically need infinite offset. But if we take infinite limits in this integral, it will be easier to take. So infinite limits. And most critical part. If you see here, there is a product of energy difference by time. And in all other instances, it is just energy difference. Mathematically, it is known, or it will be known to us, if we have more time, that there is a good table integral. When you have sine square of x divided by x square dx, it will be pi. So we are going to identify this integral, take it, and then everything will be good. How can we identify this integral in our writing here? What is x? Huh?
Omega 1 and minus something.
So one suggestion was to use x equals omega 1 minus omega. Any other suggestions? Are we happy with this suggestion, or we should look more careful? I was falling in this trap.
Divide by 2.
Huh? Divide by 2,
Over
good.
2.
Divide by 2, what else?
T.
Yes, this little letter T is critical. So right now, although our main goal is to explore dependence on time, when we call mathematician inside ourselves to take this integral, time is not part of the calculus. It is a parameter, it is a constant. So here, T is a constant. But we need to treat this constant fairly. So we need to have if you want to use the table integral, or even if we take it ourselves, we need to have the same variable as an argument of sign, same argument as a denominator, and same argument as the integration variable. So this will be our new integration variable. Which price do we pay in order? I apologize to those of you who are really quick thinkers and can imagine the answer immediately, but we better go step by step. So, what is the price of using new integration variable?
T over 2 over T.
Yes. So let's show it in a very slow steps. So everywhere where we have this old variable, how can we convert it into the new variable so that we do not damage the equation itself? We need to keep the same equation, so change nothing, but bring it into a new variable. So if you want T by 2 as part of it, we need to multiply and divide by the same factor. Multiply and divide. Okay. What if we used to have d of omega 1n minus 1? We also multiply and divide by this factor, right? So I know it is almost a kindergarten, child steps, but let's do them carefully. So how do we change this final expression? Not final, but so constant. This is not velocity of light. It is just constant that keeps this h bar pi whatever we need. Density at the resonance condition. Matrix element of transition squared. Integral from minus infinity to infinity. So we have 2 over t differential 1 omega 1 minus omega times t divided by 2 sine square of 1 minus omega times t divided by 2. Here omega 1 minus omega times t divided by 2 square. And since we committed change of we made this change to the denominator here, we need to put 2 over t square nearby, right? Correct? No errors. No one objects, which is equivalent to no errors in this community. So the time pops up out of this function of this time dependence as an explicit. So it pops up in the first power from the integration and once from the denominator. And then they cancel each other, and as a result, we do have factor of t over 2 that we can also put up front of the integral. This is most important result of our today's meeting. The rest are general introduction and technical details, but this is critically important. So we get that P of E T, so constants, density of states, transition matrix element square times T over 2, and then the definite integral from minus infinity to infinity sine square x over x squared dx. So since it is the definite integral, it doesn't depend on time. And we can show that it will be equal to constant, let's say pi, if you believe it. If you do not believe, we can check, either by going to Wikipedia or working it out for like 15 minutes. But then we have constants, we have density of the final states, we have transition matrix element, and we have time in the first power. So before, when we were dealing with discrete levels, from one level, like two-level system, from one to another, it was t squared for population. Now it is t, and this follows from transition to continuous limit, and this dirty games with change of variables. But now we did prove that population will change linearly, and if we will take the derivative, dt, which you can call rate constant, it will be equal to this constants, density of states at resonance times transition matrix element squared, and that's it. Because t disappears. Yes, y over 2. But we do not have dependence on the variable on t. So this t will disappear when we take derivative. And this rate is very general, so it is applicable to a very broad range of applications. Whew. Which applications? If any suggestions? I know that you are able to give 2 examples. One example, if it is Sam, will you help us? What is one of the applications of the Fermi's golden rule?
They use scanning tumbling microscopy.
Right? So when one has initial and final states, and if they are in resonance, there is a transition and it goes linearly. Many things generally about conductivity, about electric current deals with this. Now, the applications that one of you will cover when, on Thursday, it is spontaneous emission. When there is a, what is a continuum? Why there is a continuum of states? So even if there are only one excited and one ground, why it will go linearly? Where is the continuum? Probably Javid will explain us in details next time. But if you do have a molecule or atom where two levels, one that we will consider as ground, one as an excited, and we prepare it in the inverse occupation. And then you know that if system is not isolated, then excited state will always convert to ground. Like it will find a way to go down, even if it is an isolated atom in vacuum. Isolated meaning no chemical bonds, but it will still be connected to something. No thermal vibrations. It's like free space. Yes. So thermal motion of not thermal. What is the right term?
Transmission.
I know that Dan can give exact formulation. Atom in free space, in vacuum. What does it couple to?
This couple to
Uh-huh.
the quantum vacuum.
Yes. Ask him if you do not agree or if he is not clear. Huh?
You're better off looking it up than asking.
Just try your best. So what is quantum vacuum? Because Javid needs to present it for the grade in today's.
It's disconnected pieces in the Feynman diagram expansion.
No. Tell for at the kindergarten level.
I don't. Well, it's virtual particles that pop in and out of existence.
Simpler.
I don't know how to
So
formulate it.
you know lasers. There are modes of electromagnetic field in the resonator between mirrors, right? And if the laser is like radiating, if it is excited, then there is some energy in a mode of a given frequency. But even if it is de-excited, the amplitude of modes of the electromagnetic field behaves like harmonic oscillator at each frequency. And harmonic oscillators, even at zero temperature, they have energy 1/2 times h bar omega. So this vacuum oscillations in each mode of the electromagnetic waves, they are spaced continuously because we can assume our universe as a big resonator with mirrors put very far away of each other. And there are so many modes, and they set up a continuum. And there is a transition of energy from the pair of levels, electronic levels, to continuum of these modes. Therefore, the approach of continuous mode distribution will be validated. One can use Fermi golden rule, and therefore there will be some, how do you call when an excited state decays?
The lifetime?
Lifetime, spontaneous.
Oh, emission.
Spontaneous emission, spontaneous radiative emission. Enough examples? Enough. So, scientific part is finished, but now there is a mathematical dessert. If you need to depart for the schedule, it's fine. I know only one of you has schedule conflict. So let's take this integral and prove that it is equal to pi. What is residue? If you didn't see this term in your calculus courses, you can just share your linguistic association. How would you which associations pop up with the word residue?
Leftover stuff.
Okay, yeah, good enough. Anyone wants to tell something more mathematical? Diane? What is a residue? He's not scared. He just. I need to use sources. It is like a question. Do you know? Can you speak foreign language? You shouldn't be demonstrate here. Of course, with a dictionary in hand. So we want to take integral dx sine x squared. This is a challenge because there is a discontinuity. There is a pole, there is a singularity, there is a 1 over 0 will be infinity. But we need to integrate. So the idea is to think out of the box. Right now, our integration variable is considered as real, and it is less than infinity and bigger than minus infinity, right? So it is one-dimensional variable that we integrate. But let's assume that there is a more general number z that is composed of this real part plus imaginary part. And then we can assume that there is a complex plane x and y, and integration from minus infinity to plus infinity is just going along the x-axis, right? Multiplying by the function, adding together. Good? No arguing, no objections. Now, this function will be 0 at infinity. And we can recast it as that it will be d x plus y sine x plus y x. So the function is 0 at infinity. So the result will not change if instead of integrating along line, we will integrate it, we will add integration along another line, which is curvilinear, which is half circle, very, very far away from the origin. So far away that, in fact, integration along this path will change nothing. So just a trick. Multiply and divide by the same, or add and subtract the same. So we are just adding 0. But now, this red stuff is a closed contour. Closed contour. And for integration around closed contours in complex plane, there are very appetizing theorems that give prescription how to take these integrals in a really quick way. So we go from linear to contour integration, and we use contour integration theorems. If it is contour integration, we just make circle around it. It is simple. And the contour integral around some contour gamma dz of function f of z is summation of residues of function 2pi 2pi over I, summation of residues of this function in the poles. So if you know what is residue, then you have the answer. Okay? Sum of residues. Sum of residues. So when you talk about residues, it is backwards. Contour integral around pole, around the point where function goes to infinity. So the contour should encircle around the pole, and it should go into the specific direction. So if the pole is not included into the contour, then the integral will be 0. And if the contour goes into wrong direction, then the residue will be 0. So 0 if pole is outside, and 0 if contour goes wrong way. Any questions or objections about this ideas? No. Good. So the trigonometric function in here can be unwrapped back into exponentials. Using trigonometry. Plus e plus z plus 1 minus e minus I to z. So sine square can be wrapped into cosine of double argument, and then it can be expanded into such form. This you can do it. I checked 10 minutes before the class. Now we are going to use these two simple rules. So we want to go from one integral to two integrals, and we know that the pole is in the origin. So therefore, we do not want the line going exactly through the pole. Therefore, we drop the contour of integration a little below. So we shift. The contour. So I'm going to remove this line by finger and redraw it at a lower position. And we can do, so this contour will go counterclockwise, and we will call it gamma plus, because variables in polar coordinates are counted counterclockwise. And we can design a second contour that will go along the same line here, but then we'll go counterclockwise and take the lower part of this plane. And we call this gamma minus. Gamma minus. So because of these two rules, the integral can be split on two integrals. One over gamma plus. So because of the selection of the right way goes counterclockwise, integral over gamma plus will be non-zero only for the first term. Plus term minus term. And here we have this term. Minus z this term plus 1/4 integral 1 minus dz 1 minus z this term. So because of the contour direction way, we have only one term in one integral, only another term on the second integral. But now we look at another rule, that the pole should be inside the contour. So the point, the origin is inside the first contour. So this one will be non-zero. And we have chosen the second contour in such way that the pole is outside of this contour. So this one will be zero. So our integral is around contour gamma plus 4 z So the idea of residues is that if you do contour integrals, then when you are on one side from the pole and another side of the pole, the function will compensate itself. And many terms contributing to this function will result into zero. So there will be a very small fraction of all terms contributing to the function that will sustain integration around the circle around the pole. And the only term that sustains such integration is named residue, remains. What remains after such integration? Residue remains. Residue remains. Now let's take the little handout. On the second page, lower line, and see a prescription. So I will just reproduce what is here. Residue of function f around pole C of the order n is limit dn-1 dz n-1 z minus c power n times f of 0. Thank you. What is n? What is the order of the pole? Basically, it is this power 2. So here we need the residue of second power in the point in the pole C equals 0. So it will be 2 minus 1 will be 1. So d dz. And now we multiply our function by z to the power 2. Z squared times 1 minus e plus 2 z squared. So z squared cancels. And then we take the derivative over the variable z. So derivative of exponential is whatever is derivative of its power. And since we are using limit z equals 0, this will be 1. So the residue is equal minus 2. So constant. We did this contour integral, and we got a constant.
Is that over 2i?
Yes. Minus 2i.
2i, wouldn't it just be I?
Hmm?
The factorial gives you 1 factorial, which is 1. Where's the 2 coming from?
But it was,
Here?
yes, 2 minus 1 is 1. 1 factorial is 1.
Yeah, but then where is, okay.
And then we use this rule, that contour integral is 2 pi I times residue. So we have 2 pi I times minus 2 pi will be pi times I will be minus times minus plus 4 pi. So I think I may have missed the factor, but we will not spend time clearing it now. I may come back when we have next formal lecture. But the idea is that the integral can be taken, the definite integral, and it will be constant. And there is a way to take such integrals even if we are away from civilization, from internet, and from tables of integrals. So when we plug the value of integral into our previous derivations, we get the Fermi golden rule, which again is transition matrix element squared times density of final states times correct constant. This I would like to announce the completion of the meeting number 15. Please consider to visit labs on Wednesday night, and I look forward to your presentations on Thursday. I'm going offline and will stay here just in case there are more questions.